What if our computers didn't think in lines of code, but in waves and patterns? More like a living system. Today, we're going to dive into a pretty radical new idea called Topo Thermo Mesh Computing, or TTMC for short, that proposes exactly that. So let's get right into it.
To really wrap our heads around why this is so different, we've got to start with a super fundamental question. How do the computers we use every single day actually think? What's really going on under the hood?
Okay, so our current computers, they're built on a world of total abstraction. They use lines of code to control billions of tiny on or off switches called logic gates. But TTMC, it just flips that script entirely. It's proposing a computer that works with actual physical fields, like a magnetic field, and it operates using these dynamic patterns called transition motifs. We're talking about a massive shift in how we even conceive of computation.
Look, our digital world is incredibly powerful. There's just no denying that. But at its core, it's a really flat model of reality. Think of it like a train. It's super fast, super efficient, but it's stuck running on this fixed, one-dimensional track, just going from point A to point B.
And here's the thing. The real world isn't a straight line, right? It's full of all this complex, continuous stuff. Waves, fields, flows. And to make our computers understand any of it, we have to flatten all that beautiful complexity into these long, rigid lines of ones and zeros. It works, for sure, but it's just not a natural fit.
So this is where it gets really interesting. This is the big question that TTMC asks. What if computation wasn't a line at all, but a landscape? What if instead of a train on a track, a calculation was more like ripples spreading across a pond, interacting, interfering, and creating these complex, beautiful patterns in real time?
This brings us right to the core idea of computing with fields. And to do this, we need a whole new alphabet. Forget the simple on or off of our current logic. TTMC introduces this rich, new vocabulary of dynamic patterns that they call transition motifs.
So what on earth is a transition motif? Well, the best way to think about it is to just completely forget the idea of an on-off switch. A motif is a recognizable pattern of change in a field over time. It's way more like a signature dance move or a recurring musical phrase. It's this dynamic, identifiable event.
And here are a few concrete examples to make this real. You've got a breathing hole, which is just a smooth, regular oscillation, or a cascade collapse, which is a sudden spike in complexity that then just falls apart. But the most fascinating part? Look at that column on the right. These aren't just random patterns. They're named and described based on how real people talk about their own experiences.
Okay, so how in the world do you actually build a computer like this? Well, the TTMC framework is designed as a stack of 4 interconnected layers. You can think of it like a recipe, starting from the very foundation with the laws of physics themselves. Let's start at the absolute foundation, layer 0, the quantum thermodynamic layer. Now, this isn't hardware. This is simply the fundamental laws of physics. It's the ultimate gatekeeper, making sure that any computation you try to run is physically possible and, energy efficient. Everything else has to be built on top of this. Right, so on top of that physical foundation, you've got layer 1, the physical mesh. This is the actual hardware. This is where those motifs we talked about are created and manipulated using some seriously bleeding-edge materials. We're talking things like magnetic films sculpted by lasers or optical circuits that literally compute with light.
Moving on up, we get to layer 2, topological dynamics. This is the mathematical brain of the whole system. It's basically a translator, using advanced math to formally describe and measure the physical patterns that are happening down in layer 1. This is how a dynamic event in the hardware gets turned into a precise, computable description. And finally, at the very top, we have layer 3, the cognitive symbolic layer. And honestly, this is the most human part of the stack, and it's what makes TMC so incredibly unique. This is where that whole alphabet of motifs actually comes from, by analyzing the patterns that people, especially blind and neurodivergent participants, create and describe when they interact with physical fields. It connects the whole system right back to human experience. So yeah, that's the crucial point. This idea of human experience as code. This is probably the most revolutionary part of this whole thing. The very alphabet of this new computational language isn't just invented by engineers in the lab. It's discovered in the rich, complex patterns of human experience itself. It's an approach that could solve problems that are incredibly hard for our current computers because it speaks a language that's much closer to nature.
And they do this through experiments like the Time Cavities Lab. In these experiments, people literally interact with a vibrating plate that's covered in sand, and they create these complex patterns with their hands. Those dynamic sand patterns are then captured and mathematically analyzed to identify those recurring motifs we saw earlier, like the breathing hole.
And this quote from the source paper just captures the spirit of this project perfectly. It's about creating a way for all kinds of human experiences, like those from the blind community, to be a direct part of designing our future technology, not as some accessibility feature you tack on at the end, but as part of the core alphabet. It's just a radically inclusive vision. Now, I know this might all sound very philosophical, but the researchers have a really concrete plan for building an actual, plausible machine. This is not just a thought experiment, it's a full-on research agenda. And they've already identified several truly cutting-edge technologies that could serve as the physical hardware. For instance, they could sculpt these 2D magnetic fields with lasers, creating energy landscapes for the computation to unfold in. Or they could use light waves to perform massive calculations instantly. It's all about finding the right physical stage for these dynamic patterns to perform on. And here's the game plan for a first deliberately simple prototype. Step 1, create a basic magnetic landscape. Step 2, try to get the system to produce that simple breathing hole motif, that basic oscillation. Step 3, measure what happens. And step 4, see if it worked and if it was energy efficient. It's a small step for sure, but it's a crucial one to prove the whole principle works. And the grand vision here, the big dream, is to create a new kind of computing that isn't just an abstract game of logic. It would be a system that's deeply rooted in the physics of the real world, a set of physically grounded and thermodynamically disciplined transitions. And that just leaves us with this one fascinating final thought. What would it mean for our world? What would be possible if our technology learned to think not like a rigid machine, but like a dynamic, adaptive, living field? The possibilities are just truly mind-bending.